in my lab.
Oh yeah, I'll check your stuff while. Do I have stuff to give back to you guys? I do. Look at that.
Here, Josh.
I just drank 56 grams of lemonade.
I'll put it over here.
It could be great. Oh, my homework? Module
Couldn't be
10,
grams, yes.
Module 10, first half.
Yeah, we did there, and then on your own there.
Do you have water?
Good.
Yeah.
Okay. Is that running?
What? Yes.
So,
And it's videoing successfully?
I just give you a drink, you know.
Yes.
okay.
Hi, Sam. Okay, the first thing that is on the top of my sheet says, warn students about a question on the test that is too easy. There's a question on the test that is so easy that entire classes have missed it because they try to make it too complicated. So, note that there is an easy question on the test. Don't overcomplicate your life.
like 0 or something?
No, it's just like,
Or like,
it
yeah.
practically states the answer in the question, and like, you don't need to run around about it. So, just be warned, there's an easy one. You don't have to take a test this week, so don't go home and
We
take
don't
a
have
test.
a lab either.
No, you don't have a lab this week, because what we do as a lab this week is just the first half of next week's lab. So
Like,
it'll be
This
2
is
weeks,
gonna be
one
an
lab
awesome
report.
week.
Like, I saw this thing, and I was like, there's only one line of,
Especially for you.
Yeah,
it made
it's,
my heart happy.
it's one lab with 2 parts, but the part that you do this week will have to be included in next week's lab report. So you can sort of start it or think about it or whatever. Did anybody bring graph paper?
I forgot. I remembered
I did.
right when I got
I
the
got
part of
for
the
everybody.
and I
I got
I
graph
don't
paper
even know
for
what I
everybody.
We have tons of graph paper all over.
I
I just-
have half
Who
of
needs
a
graph
sad
paper?
sheet of graph paper here.
I do.
Here, mine looks better.
You
Okay.
just need one
Graph,
piece.
yes,
Oh,
Josh.
thank you, Josh. Hooray.
Josh,
Okay.
you get
Josh,
extra
over
credit.
here. Over here.
Josh, you get 1 point
I'm
for
down.
every piece of graph paper you hand out.
Oh,
So-
I'm
I'll
okay,
take
just
graph
fine.
paper.
He does.
I need one.
Everybody?
You can have it.
Yeah, we were.
I need to
Josh?
put more in my
No,
thing.
we're done.
Chemistry
Oh.
starts a lot of
Well, yeah,
graphing.
I know.
I already got. I took his.
All right.
Wait, I need a
So, what am I talking about?
Thanks.
What are we
Stephanie
doing
brought graph
today?
paper.
Okay.
Because he's smart
So-
or not.
Today we're going to talk about periodic motion. Now you've already seen several examples of periodic motion. Does anyone know what are some examples of periodic motion? Okay, we've seen pendulum. And any other examples of periodic motion?
20 grams of my lemonade is evaporated.
I think that scale is very inaccurate.
Did he just bark? Sounded like he barked.
So, hi Sam, sorry. Any other examples of periodic motion besides the pendulum that we've already looked at?
The rope we spun around her.
Yes. Any sort of uniform circular motion would be a good example of periodic motion. Orbiting planets, constant velocity spinning, well, constant speed spinning. And today we're going to look at a new system of periodic motion, a mass spring system. We're going to do a lab, start today, finish next week about the mass spring system, which is sort of fun. And a lot of it is very similar to the stuff that you learn about pendulum. Pendula? I don't know. Anyhow. So, when you're looking at a mass spring system, let's draw one. So, in lab, we're going to suspend our little spring here. It'll have a mass hanging off of it. Okay. So, obviously you'll have the force pulling downward. It'll cause a displacement in the spring, right? Your spring will displace from its normal length a certain amount, right? And when you displace a mass on a spring, what does it want to do?
Recoil, like go back.
Right, it wants to kind of recoil, it wants to kind of go back up. And so the spring will have a restoring force. The restoring force is always pointed in what direction?
Opposite.
Opposite of what?
Sorry.
The push-pull, the thing that's pulling it or pushing it away from what it was.
Okay, so whatever the normal length of the spring is, If it is compressed, then the restoring force is going to want to return it to its normal length. If it's spread out, the restoring force is going to want to return it to its normal length. So the restoring force is always going to be opposite of the displacement of the mass. So if your mass is displaced in this direction, then your restoring force will be opposite. If your mass is displaced in this direction, your restoring force is going to be opposite. And that can be described mathematically as Hooke's law. Does anyone remember the equation for Hooke's law?
Yes.
P. No.
F equals negative K delta X.
Okay. And the negative is attached to the constant K because it's always going to be opposite the displacement. The restoring force is always going to be opposite the displacement. So F has to be negative if displacement is considered positive. Hooke's law looks a lot like the equation for a line,
Y equals
as long as what?
Equals 0.
As long as B equals 0. Now, a spring always will have, when you graph a spring's displacement versus mass, you're always going to go through. There'll be no displacement with no mass, right? So the B is always going to be 0 because you always start at the origin on that graph. Every spring has a K. Every spring has a different K from every other spring. Each spring has its own unique K. So in the lab today, I cannot stress enough that the spring you use this week has to be the spring you use next week. If you use a different spring next week, then you'll be using a K that doesn't go with your spring.
How do we know the systems?
Well, we need to like label our springs or attach some weird clippy thing or in some way make sure your spring is still your spring next week. So make sure you do that because I might forget in the next 3 seconds. But you want to know your spring because your spring has a unique K that won't be any other spring's K. And so today in lab we're going to find the spring constant K of your spring. And then you have to use it, the same spring, to find all the other stuff next week. So anyhow, we just talked about periodic motion. What would a definition of periodic motion be?
Something that happens over and over again.
Okay, a motion that happens over and over, repeats itself. Okay, so very similar terminology with mass spring system as pendulum. Okay, you have an equilibrium point, which is if your mass is hanging from the spring, it is hanging at an equilibrium point, right? You can displace the mass, and that would, as far as you displace it, that would be its amplitude of motion. And the restoring force is always going to point toward the equilibrium point. So if you displace it this direction, the restoring force is going to point toward the equilibrium point. If you displace it in this direction, the restoring force is going to point toward the equilibrium point. Always going to be opposite of displacement. Let's see. Your spring will have a K, and K describes the strength of a spring. The larger the K, the stronger, the less easy to displace a spring is. Your best bet in this particular lab is to use a spring with a small K. Using a spring with a big K makes your... Right, we would have to get fancy. So if we do 3 lab groups today, we may have to get fancy. You two will have to be creative. Actually, Andrea's brother is the one that came up with the solution. We had a very tight spring with a K that was too large, and we didn't have another spring that year. So he hung his 2-liter, which is a larger mass than the lab calls for, and the lab totally worked, but he had to keep drinking to decrease the mass throughout the experiment. So I think we almost drowned him, but you know.
Yeah, you're gonna have to get drowned.
We can pour it down the sink. We didn't have a sink that year.
I can drink it.
Okay,
Nice.
but don't do it now in case we need the mass. Of course, we can always add distilled water or something, or we could just hang the water jug off of it.
Maybe there's the water jug.
I'm not drinking all that.
we can dump that out.
I'll
But
drink out of
anyhow,
it.
hopefully I've got 3 good springs.
I like it still water.
Or the ammonia, you know.
It tastes good.
What other type of water do you drink?
Tap
Salt
water
water?
has stuff in it. Distilled water has no like dissolved minerals, so distilled
When I was
water
little,
tastes
I
like very
used to
flat.
like bath water.
Wait.
Wow.
Not in the bath. That's disgusting.
Yeah, you
like out of
drink
the
the
faucet.
bath.
Like out of the
I was gonna say,
Like
and
slime.
YouTube.
bath.
Yeah, she
When you
drinks
go
bath
to
water.
Like, never drink out of the bathtub. That's disgusting. But like the water that comes out of the faucet.
No, actually, when
Shouldn't
I'm
be the
really
same.
thirsty in the middle of the night, I go to my
It's
sink in the
different.
bathroom and just get water
My
from
kids
there.
do that too.
I'm
They
like, okay,
actually
if I
make
die,
water
I'm
from it,
fine.
touching it.
Oh,
I do that during the day.
Yeah.
everyone does that.
I don't do it out of
I
the,
do
the
actually
kitchen
not do
sink because
that,
that always
but-
tastes weird.
We have a little filtered
Oh,
sink spot.
yeah.
Spout.
Okay, so not only are pendulum and uniform circular motion examples of periodic motion, but both are actually examples of simple harmonic motion. And what do we know about simple harmonic motion from what you read this week? And Matt's like, please let it be on the stage.
I don't remember anything.
Period is independent of
I don't remember anything.
Okay, in
Very
simple
good.
harmonic motion, period is independent of amplitude. So what does that actually mean in real life?
I have no idea. I was
Means
gonna ask
to
you.
read.
Yeah, I don't
Well,
know.
if you bring out this much
Yeah.
or this much,
I read
it
it
still
like-
didn't take the same amount of time to bounce it around.
Exactly. Okay, so listen to this.
Really?
What simple harmonic motion means is that,
If you pull it
In-
out more, it'll just go faster.
Yeah.
but it takes the same amount of time. So where's my spring?
No,
In Newtonic scheme, there's like 5.
Do you even open that book?
Ironically,
She's like, you
we're
alright?
supposed to wear
Can I have some water? I'll
I
fill it
didn't
up.
even know. I
Let's
didn't
see.
I'll just drink all of it and go fill it up.
Yeah,
Alright?
I'm gonna hang something off of this
Sure.
spring and see what
My
happens.
mom is gonna wear my
Let's see.
navy sweatpants, but my mom got that. I remember you look so ugly.
What?
Okay,
That's
so
my mom.
the
My mom's
when you
crazy.
say simple harmonic motion has an amplitude that is, or I mean a period that's independent of its amplitude. Well, what's period?
The time it takes to do one rotation
Okay,
or whatever.
so in
Wait, how much
spring
can that
system-
spring hold?
3,000 pounds.
A lot.
No,
No,
you're lying.
Not at all. Okay,
3,000
in a mass
pounds,
spring
who's died?
system, the period is when it goes from its displacement all the way up through and back. So when it goes and returns to where it started, that's one
This is gonna be
rotation
such a cool
in a mass
I
spring
love
system.
spring.
Who
So,
doesn't? Like the
know,
things
right?
well,
like
this
pencils.
isn't heavy enough.
Like I used to like.
Right.
Yeah. I used to take them and shoot them and get them stuck in the sand. With the spring and then shoot the pencil. And
My brother used to sit in Panera and he'd take the little things that go in the fountains and shoot them up in the ceiling and he had like
Oh
fun.
my goodness.
He
that's
got in
awesome.
trouble.
Yeah.
I used to throw those sticky things you
Okay.
put on your.
So this will displace
glass
it
and
more.
stuff.
Okay, I've
Throw
got a
them
bigger
on.
mass. So my one
Or go
period
back
would be if I
and make
displace
really
it
wet.
and then it has one bounce. So up and back down to the amplitude of motion. I cannot hold this, it hurts. Okay, so when it says that in simple harmonic motion, the period is independent of the amplitude.
Oh my
That
gosh.
means that the time it takes to bounce,
nudes.
if I displace a little bit and it bounces, that time for one bounce is exactly the same as if I do this.
See, when you guys were talking about it, I was really confused because I was thinking of hard spring.
It looks like a bungee cord,
That makes
like
a lot more
bungee
Right.
jumping.
So, actually the
That's been
end
developed.
point of
Right,
next
okay,
week's
so you
lab
figure
is
weight.
going to be that we
You're
prove
really-
that the period of this
Okay.
is independent of the amplitude of
That's
its motion.
pretty much like bungee jumping.
Yes, we're bungeeing a little bag of sand or
It's
beans or
awesome.
whatever you get.
I'm gonna just think about bungee jumping the entire climb.
And so
Joking.
today what we're going to do is find the spring constant of each spring, hopefully not stretching it out so that the fourth spring is completely.
How much so it could hold his jug?
Well, this spring should be just right to hold the 650 Newton force that the lab calls
So
for.
how many pounds could it
Or
hold?
whatever the force of the lab calls for. I got a good spring
Is
for you
this
guys.
so? The smallest one is the one that
This
can
spring.
hold the most.
This spring is much tighter, has a larger K, larger spring
So that means it can
constant.
hold more.
It can
So,
hold 5,000 pounds.
You're lying.
so I
Navy
would require
SEAL
a
me.
larger mass to really do an experiment with this. Wow, somebody like made the end of my spring funny. So, anyhow, we may need to MacGyver some more clips today or something. I have paper clips in my bag, so.
This is gonna be
Um,
so awesome.
This spring has a larger K.
Who
so-
doesn't think
It will have,
this?
actually it works. It doesn't completely it doesn't return to completely closed. So this spring will actually work.
So it could hold that jug.
Yeah.
It would
So
definitely.
awesome.
But regardless of the displacement, its period
I can't even
should
hold that
be
jug, it's so
independent of the amplitude that I displace it.
Shouldn't we put it somewhere
pick it
where our
up, it's
arms not
too
moving,
weak.
like
Absolutely, and
practice
that's
in the
why
table?
we've got ring stands, we've got rollers. If we do 3 lab groups, I only have 2 ring stands.
We
so
could put it
somebody's
on
gonna
that
have
then.
I think it's not long enough. But I've got enough rulers that we can suspend one from a ruler and it should work. Yeah, but it'll hit the wall.
Oh, yeah.
But
Okay.
Um,
I went and wore it down. And
Okay, so just like when we talked about our car diving off the desk and what's happening in the Y direction, what's happening in the X direction, you need to know, like everything there is to know, or about the pendulum, you need to know everything there is to know about the mass spring system. So, when the mass is at the amplitude of its displacement, what is potential energy?
Wait,
Everything.
what? Can you repeat the question?
When the mass is at the amplitude of displacement, what's potential energy?
100%.
Full potential energy, maximum. And kinetic energy?
Nothing.
None. Okay, so then if it does one bounce, where does it have maximum kinetic energy?
At the equilibrium.
Equilibrium point. And then when it gets to its other amplitude at the highest point, then what about potential and kinetic energy?
Same as the other two.
Which is?
None kinetic, everything potential.
Okay, so at either amplitude you have maximum potential energy, 0 kinetic energy. At the equilibrium point you have maximum kinetic energy and no potential energy, right? Right?
Right.
Yeah, yes, ma'am.
Okay. Don't ever ma'am me, that's
Oh,
painful,
sorry.
thanks. Okay,
Yeah, Sam,
so
don't ever
not
say
only
ma'am.
do you need to know about potential and kinetic energy, you also need to know about the velocity at these points. So what is the velocity at either amplitude?
0.
0. Velocity is 0 at the amplitude. That's where it's turning around, changing direction. It has to reach 0 at some point to change direction. How about velocity at the equilibrium point?
Super duper.
Maximum. The highest velocity you're going to get is going to happen right at the equilibrium point because it's going to be speeding up, hits the equilibrium point, and then as the spring's compressing, that restoring force is now pointing against the compression. So it's going to slow down, speed up until it gets to the equilibrium point, slow down, speed up, slow down, speed up, slow down. So velocity is 0 at the amplitudes and maximum at the equilibrium point. How about acceleration?
What about it?
Well, where would you have maximum acceleration?
Oh, I remember this one. Was making me confused.
The amplitude
Yeah.
Why?
of movement.
'Cause
Why
the
is
spring
acceleration
trying to
maximum at the
pull
amplitude?
it.
Because it's had all of the, I don't know, it's had
The
all of
spring
the
is pulling
momentum
it
going up.
one way, and gravity's
One.
also pulling it, so it's got 2.
Right.
No, I don't remember the reason, but it was at the amplitude.
At
It
the
was
amplitude,
confusing
the
too.
restoring force is
It's
pointing toward the
completely in a circle.
equilibrium
And
point.
then it
Ninety.
hits
So
that.
the full force of the spring is pulling, right?
Yeah.
And then at the other amplitude, full force of the spring. Of course, it's cooperating with gravity at that point, but just considering the spring and not gravity, you have maximum acceleration at the amplitude and 0 acceleration spring-wise, not gravity-wise, at the equilibrium point.
Would there be more velocity going down than coming up?
Yes, I would think that acceleration would be bigger
Oh.
going down than up, just because gravity is in addition to the spring.
would do
Feels like the
So if you're in
stretch
like space and did that, when you pull it out, the spring would pull itself back to the equilibrium point, but would it do anything after that?
If you're in space,
There's so
it would, because you would still have kinetic energy, so you'd still have momentum, so you'd still keep going, and then the
Okay.
spring would, want to, the restoring force would push it back toward the equilibrium point. So I think it would oscillate. This is oscillating, by the way, oscillating
So in a vacuum, it just keep going forever.
in a vacuum.
Has-
Well, it depends on gravity too.
If there wasn't gravity in a vacuum.
That's
No
space.
gravity in a vacuum.
But
Because-
if there's no gravity, it wouldn't pull it down, to be honest, right?
You can have a force independent of gravity. I
But
can
if
apply a
you
force.
weren't holding it at all,
Well, there'd
Well,
have to be enough
you're not
friction for
pulling
me
down
to
on it.
hold it, right?
well, you're not pulling down, you're just holding it like that. It would,
Well, something
Like-
would have to start it. I mean, something would have to apply the
Because in
displacement.
space, it just went like, woo, and float away.
But once you
Ugh.
started the system, it should keep going if you don't have air resistance and you don't have gravity.
Because the energy couldn't be lost.
Right. But we have to do some math because you have to make sure momentum is conserved, kinetic energy is conserved. That could be complicated. I have to think. No time to think now. Okay, so because it's a simple harmonic motion, the period of a mass spring system only depends on the strength of the spring and the mass of the object. Okay?
But aren't you affecting it?
Well, yeah, I can't help but move my arm. It's hard not to. I'm trying hard not to. So,
First, my mom.
That's kind of mesmerizing.
okay, but it doesn't depend on displacement. It only depends on mass and the spring constant. And then, does he do the derivation in the book where he shows you why amplitude cancels out in the math? So you can look at that.
Unless you have like IQ of Jesus.
Crazy.
You can understand that. That's not hard. I understand that. If I
On the
look at
test,
it,
are
I'm
we
an-
supposed to explain that?
I will look.
Well, he says you don't have to understand it.
You don't
so-
have to understand it. Good. Good news. All right. What have I not talked about?
The little thing with the flashlight and sliding ball
Oh, okay.
in figure 10.1.
Oh,
Okay,
the
so-
one-dimensional.
Right. If you have,
Are you gonna do the experiment though? Or is that next week?
we're gonna do part of the experiment. So if you have something, if I were perfectly drawing this circle, if you have a flashlight shown on something in uniform circular motion, and you look at that shadow, then what you're seeing is exactly like a mass spring system, right? Because the reflection of the mass traveling around, if you see that shadow, you're gonna see something going up and down, exactly like a mass spring system. Okay? 'Cause
Just
you're
like when
gonna
I was,
see,
when we did that experiment with the spinning thing, I had the really short string, and you can only see it when it was like here and here. You can see it in a circle.
it looks like it's just going like this.
Yeah.
Well, that's because
Because you can't
the
see.
same on both sides.
So how about if this is true, if anything that's in simple harmonic motion really does have a period that's independent of its amplitude, then how would that apply to a pendulum?
Your clock, your grandfather clock will always keep the right time, even if you bump it a little bit, so it goes a little better.
Okay, so your grandfather clock, the period's independent of its amplitude, so if
You
I
have to wind them up
displace
though.
the pendulum here, well, that's because there is air resistance, so it
And then
does
slow
have
down
to,
and then you have to wind them up again.
it does have to have a certain amount of
So,
force.
if you took your
Got it.
grandfather clock and
Ruining
put
Sucked
the
the air out.
the thing that the
I wish I had a grandfather
pendulum
clock.
is in,
You have one?
made it a vacuum chamber.
And
That would work a whole lot better.
My grandma does
But
too.
no vacuum's perfect, there's always.
It always
some
goes
air.
off every hour and like, shut up, I'm trying to watch a
I
movie.
always wanted
For
a
a
cuckoo
pendulum,
clock.
simple harmonic motion only works at a
Scare the crap out of
displacement
me.
angle of what?
No, like
Big
What?
displacement, okay, so if you have a
It was
pendulum,
like 30 degrees or less or something.
is it
That
30
one door,
degrees or
and
less,
then
20
when
degrees or
the
less?
other door.
Something like that.
Something like 20 to 30 degrees, a small angle. For a pendulum to exhibit simple harmonic motion, you must have a small angle of displacement.
Which is why the
So,
grandfather clock is like this instead of like that.
right, you don't want your grandfather clock to be displaced like 50 degrees like this, because see how it bounces? Because it does, yeah, partially drop. But if I have just a small displacement, then it will, well, other than the bouncing, it will kind of act like a pendulum. If it were really a string, it would be better. Okay, so say you're on a swing
It's
set.
against the wall.
You're like a pendulum on a swing set,
You
right?
go too high, you drop.
Well, but as long as you're not going too high, if you're in simple harmonic motion, then how about the time it takes you to swing? Is the time it takes you when you're first starting to swing to complete one swing the same amount of time as it takes you when you're going really high?
Yeah,
Yeah, each,
because you're going slower, but not as much distance.
right. So anytime you're a pendulum, you're going to exhibit simple harmonic motion. You're going to have a period that is independent of your amplitude.
Is there such a thing as complex harmonic motion?
Everything's complex because you have to, I mean, we're not accounting for air resistance. We're not accounting for, I mean, a person shifting in a swing. We're not accounting for a whole lot of stuff, actually.
Pumping.
Right, we're not accounting for motion of the earth. Like a real pendulum, actually, the rotation of the earth and stuff causes a real pendulum to actually kind of wobble a little. There
My
are
dad had one of those
YouTube
at
videos.
his college. It was like a scoop on and you could just push it and it was like one of those dangly ones and it would just make cool designs.
Yes,
I would say.
Because he was an engineer, so in the engineering building was like, yeah, it was so cool.
those are really neat.
There was somebody I know had like one of the little ones, was like this tall, and so I was playing with it. But after I like spinning in a circle, and after a while, it would just make a straight line. It would go from making a circle, making a straight line, and it couldn't do anything else.
But do remember that even though the amplitude doesn't affect the period, the mass does. If I change the mass, it's going to change the time. Okay? If I change the mass, and we're going to see that in the lab. But I'm thinking
But
the
no
best
rab
thing we
light
could
up
do-
right up this week.
Well, what we do in the lab this week will be included in
So we just
one
need to pay
lab report
attention.
for next
And
week.
write up what we
Just
learned.
pay attention.
This graph,
we don't have to
the
your
graph will be included in the lab.
Okay.
Because the graph is the way that you calculate K, the spring constant for your spring. I don't know a way to calculate it without graphing it. Let's do a couple of problems and make sure we save time for lab. What time does this class end? We have an hour?
We have 1 hour.
Okay, so we can do math and stuff for about 30 minutes. Okay.
I don't know if I can save my lemonade that long.
We can always add. to
Wait,
it.
how much longer do we have? Like an
Might have a
hour?
packet of something somewhere.
Huh?
A mass spring
One.
system. I don't even have a drink.
Really?
A mass spring system, this is number 1 on review questions, is displaced from equilibrium by 5 centimeters. So that's one thing you'll have the fun of doing. Let's talk about when we displace that mass spring system 5 centimeters, right? So when you're measuring the spring, you're going to measure from the first loop, and then you're going to measure a mass spring system from the exact center of the mass, which is nearly impossible to do when you're dealing with a bag. So I'm totally fine with you measuring from some other given point. I mean, I think it's easier probably to get the bottom corner or the top corner or some place, but you're going to displace 5 centimeters. So let's say 1, 2, 3, 4, 5. And then obviously you don't want it touching, right? But I just displaced my mass spring system 5 centimeters. The period is determined to be 3 seconds. So what is the period if the thing is displaced by 15 centimeters?
Josh.
Yeah, Josh. If I look at it, if I displace it 5 centimeters, it has a period, right? A time it takes for one oscillation.
Right.
If I displace it more, what's the period? Ooh, I can't displace it that much, but what's the period if I displace it more? This is simple harmonic motion. Period is
This.
independent of
Mass.
No, period depends
It's
on
the same.
mass.
It's the same though, right?
Period's independent of displacement, of amplitude.
Wait, so you're saying that you... I don't get it.
Okay, if I displace this a little bit, it has a period.
Right, and
If
what
I
is the
displace
period
it a
then?
lot, it has a period.
Right,
And those two periods are,
equal.
yep,
Oh, that's it? I
yep.
just didn't understand.
So I'll read the question again. In a mass spring system, if it's displaced 5 centimeters and its period is 3 seconds, what is the period if it's displaced 15 centimeters? So what's the
8
period?
seconds.
What is it?
8 seconds?
3 seconds.
3 seconds.
The
I
period-
said 8, daggone
If the
it.
period's 3 seconds at this displacement, then the period's also 3 seconds at a bigger or smaller displacement, because the period
Okay.
is completely not going to change with amplitude.
It's not going to change with amplitude.
Yep.
Is
mass
that the
spring
obvious
system.
question on
There
our
is a-
test?
I don't know. I just have a note here to tell you that because I had like a whole class miss it.
I don't think a whole class would miss that though.
That's true. Unless they were really dumb. Or small.
Yeah, pretty
Like 2
much.
people.
Oh no.
Do the face,
All right,
Josh.
I will ask a dumb question. I'm about to ask a dumb question.
Guys, pay attention. It's on the test.
Hold on.
Oh,
Pay attention.
okay.
All right.
Should I write this down?
Yes. If my
Write it down for
amplitude is 15 centimeters, how far from the equilibrium point is the mass spring system displaced?
15
7.5.
centimeters.
Yeah.
That's easy. Same number.
If my amplitude is 15 centimeters, then my displacement is 15 centimeters. Seriously. That's a sad and it's not even at the beginning of the test either. It's like in the middle of the test. So you don't expect to be hit with a ridiculous question at that point. I mean, they all missed it the first year. They all did some big old calculation and got some big old answer. And I'm like, oh.
Test.
I might have missed it too. I don't remember. Number 2. What is the definition
So
of a
15
response?
centimeters, just remember that because that's
No, that's not the number.
Dang!
Totally not
Blast
the
it.
What's
number.
the question again?
At least, if you have a displacement of 15 centimeters, what's your amplitude?
15
Oh
centimeters.
no! Mr. Science is about to die.
Oh, I have another battery. Bye, Sam.
Bye, Sam. We
Bye,
love
Sam.
you. Ah, just shared.
Here's Andrea
Nancy,
missing.
bye.
See what I'm talking about? Every 5 minutes.
I'm just paying attention.